Yes. So I'll probably spend like 15 or 20 minutes revising what uh, we talked about. So, okay, so sequence is simply okay. So I should define. So we'll talk about real sequences, but this could be okay. So we could have any non-empty set. So, uh, so let X be a non-empty set. And then we can define a sequence on X as well. Okay, I'll use so it's okay. It's a function from naturals to X actually, and so AI corresponds to what f of I would be, and so each of these AIs belong to X. So that's really it. We'll mainly talk about real sequences, but maybe we might see rational sequences or natural numbers or natural sequences or integers, etc. Right? And okay, so it's not like a sequence has to start from the index 1. It's fine to define a sequence that starts from the index -5 or +100. Or you could also define sequences both ways. You would just have to modify the definition. It's quite flexible in that sense. Okay. And then we define what convergence of sequences means. So so what is the behavior of this sequence as n becomes large? So well, okay, one particular sort of behavior. What so we say that the sequence converges to some L. So okay, L is a real number here and everything is real right now. And so we say that this converges to L if okay, so here's the intuitive idea. Let's say we have this sequence
Yeah,
one,
since
four.
this is sequence is a function, so it must be similar to function because for larger values, this must converge to some value.
Yes, but it's just that when we look at limits of functions, often we vary x continuously to something like infinity, but here we'll vary it discretely.
Yeah,
So
yeah.
it's just a
Here
little,
it is the discrete.
yes. Yeah, it's similar to functions, but anyway, let me define this. So notice that intuitively you all know that this converges to zero, right? So, but just to formalize what it means, note that, okay, so no matter what epsilon I give you, eventually all terms are at most epsilon distance from this limit, right? So let's say I give you something like 1 over pi raised to 1000, right? So then you can find a term such that everything after that is such that the difference between all any of those terms and zero is at most this much, right? So I mean, say for example, 1 over 4 raised to 1000 works because everything above that, the difference between any of these terms from zero is at most this. So I don't need to find the exact number as long as I can find some number. So this is a there exists. Just to make sure you know the symbol, this is for all. This is there exists. So that is for all epsilon more than zero. That is no matter what epsilon I give you, which is positive, there is some term such that eventually on at that term and after after that, I mean, any sequence that comes after that has this difference at most epsilon from this limit L. Yeah. That's what convergence means. Okay, great. Uh, okay. And there are certain properties of sequences that ensure convergence. So here's one property. So properties guaranteeing convergence. Convergence. The first property is this. If the sequences is non-decreasing and is bounded above. That is, every term is less than equal to something. There's some upper bound on each term, but the sequence is non-decreasing anyway, then it converges. And the intuitive idea is this. Well, okay, we don't exactly need intuition. Okay, this is called monotone convergence theorem. And let me just sketch out a proof briefly. Here's the idea. So think of this as like the number line drawn, the number line drawn vertically. So each term has some upper bound, right? So this is some upper bound. Yeah. And now you look at the smallest upper bound. So there exists a smallest upper bound. That's okay. So before that, it's important to know this property of reals. So this is called the completeness property of reals. So let me define that first. Property of reals. Let S be a set, a non-empty subset of reals. Okay, which is non-empty, such that S is bounded above. So say S could be the set of all negative reals or even negative integers, or it could be the set of numbers such that the square is less than 2 or something like that, right? So such that S is bounded above. Then there exists, okay, so there exists a number uh, which I should call L, such that these true properties hold. L is an upper bound on S. For S, uh, for any number less than L, L prime is not an upper bound, which means L is like a least upper bound, right? So this is the property. No matter what non-empty set of reals you take, which is bounded above, there is some real number which actually acts as a least upper bound. So it seems sort of obvious, but uh, this is not true for rationals, for example. Uh, so this is L and R. So is not an upper bound. So if you replace this, okay, so if you replace this and this with rationals, then it's not true. So try to figure that out. Upper bound for S. Upper bound on S for S. I think we've seen both. Okay, so that's what we'll use to prove this property, this first thing, that this is enough for convergence. And the idea is to take the least upper bound. So since we know that the sequence is bounded above, consider the set containing all terms of the sequence and and take out the least upper. So there is some least upper bound, right? So let's look at that. So yeah, now we're back to the proof of the first property. So we have some least upper bound. And so here's the idea. So we have these terms that are non-decreasing, right? So maybe it's constant for some time and then it increases, etc. Right? The idea is that if I sort of reduce this bound just a little bit, let's say I reduce the bound here, then there is some term which will be more than it, right? Because that's the definition of least upper bound. So because so since I've taken the least upper bound, if I reduce the upper bound even by an epsilon, then there will be some term that will exceed that bound. And so the idea is that no matter,
This is by completeness.
yes, this is by completeness. So since I've taken the least upper bound L, so any L prime which is less than L is not an upper bound. So So this is the, oh god, this is the true bound. I mean, this is the least upper bound. I'll abbreviate it as LUB. This is any other real. This is our L, and this is the L prime. Yeah. And so once there is some term that has exceeded L prime, everything eventually will also exceed L prime. And so now note that the difference between, so if I had taken this L prime to be L minus epsilon, then note that after this term, the difference between L and each term of the sequence is also at most epsilon, because we cannot go back, we cannot go down again, and we cannot go up because this is an upper bound. L is an upper bound, so we can't go more than L, and we can't go less than L prime because otherwise the sequence will not be non-decreasing. And so all terms of the sequence are trapped between this interval, and so they refer by at most epsilon. And
Yeah,
this
yeah.
is true for any epsilon. Yeah. Okay, great. And so a similar property holds where I can sort of replace decreasing with increasing here, and bounded above by bounded below. It's the proof is similar. And so instead of least upper bound, I'll be looking at greatest lower bound. And note that if least upper bound, if this property is true, then it's also true for the other thing because I can just take the negative of the set or something. Right. Okay. Good. Um, okay. And then we saw this second property, um, which I'll just mention briefly, which is called, actually, maybe I'll not mention it for now. So, okay, I've just mentioned one property. Okay, great. And just trying to see what, okay, and we we also saw one more definition, which is, so since we saw sequences already, we should also talk about series. So a series is sort of just the sum of the first n terms of a sequence. So a series looks something like this: a1 plus a2. I mean, okay, technically we can view it as a sequence because I can just define a2 as this whole
So,
thing.
so it's like a series is defined like this. First term is A1, then second term is the sum of first two, then third term is the
Well,
sum.
yes. So the series, well, I don't. Okay, so given a sequence AI, the series corresponding to the sequence is corresponding, we call this A, corresponding to,
Yeah, yeah. This is you don't needed to write this, but I was just asking that series is defined like this because
yes.
it's like in smaller classes they teach arithmetic series, and those are literally sequence. So they should not use sequence and series interchangeably, right?
Well, okay, we call it the series corresponding to capital A. So a series is well, a series corresponding to a sequence A1, A2, A3, etc. would be the sequence A1, A1 plus A2, A1 plus A2 plus A3, etc.
Yeah.
And
Yeah.
it's also written like this: summation AI. Sometimes you just write this, so, and it's sort of understood. So so maybe the definition of series is different. Maybe I don't remember it correctly, but it doesn't really matter. Like, so
Yeah. Yeah.
the
Mm.
point is that we're trying to also analyze the sum of the first n terms, not just the nth term. And so all these definitions of convergence, etc., will naturally extend, right? So when I talk about convergence of the series 1 plus half plus 1/3 plus 1/4, etc., I mean to say that we look at the sequence 1, 1/2, 1/3, etc., and then we look at the convergence of the series corresponding to it and not the sequence. So, okay.
Mhm. Okay. Okay.
Yeah. Uh, okay, great. Um, and just give me a minute, I'll be back. Yeah, okay. And then we just saw one more definition, which is, okay, just in time, which is a subsequence. So, given a sequence AI, a subsequence, okay, we can technically define it to be an infinite subset of the set of naturals. So basically, what it means is I can just skip terms of the sequence. So I'll just take an infinite sequence, but I can just skip some terms of the sequence. That's all it means. So a subsequence is subsequence of this. Uh, so I'll just use capital A to denote this every time. So uh, is a okay is well it's okay it's a subset. It's not just the subset. Okay, it's an infinite subset. So it's an infinite subset of n along with. So it's actually the corresponding terms of the sequence. So the definition is not exactly correct, but it's fine with the as long as you understand what the subsequence means. Corresponding terms from A. So basically, a subsequence looks something like this: A index 1, index 2, index 3, etc., where I1 is less than I2 is less than I3, so on. Basically, I just skip some terms of the sequence, but I do it in order. So I can't take A4 and then A2 and then A6 and then A1. That's not allowed. Has to be strictly increasing. So the sequence itself is also a subsequence of itself. And so, as an example, if I have the sequence 1 half, 1/3, etc., then say 1, 1 by 4, 1 by 9, 1/16 is a subsequence. Yeah. But 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 1, 1/3, 1 half is not a subsequence because I skip a term. I mean, I interchange terms, so I can't go from half to 1/3 to half. And this is also not a subsequence in fourth or something because I cannot repeat terms. Okay, great. And so another okay, and we also saw this that okay, uh, if a sequence converges to a limit, then any subsequence of it also converges to that same limit. So if AI,
Yeah, this is very intuitive.
yeah,
Yeah, because this is like obvious because we have just excluded some terms.
yes, to L, then any subsequence of it also converges. L, right? And also note that if I sort of okay, what is also true is that this also true is so suppose I have a sequence A1, A2, A3, so on, and I sort of partition this into finitely many sequences. So here's what I do. Maybe I have just the odd terms first, A7, etc. And then I have okay, then I have the even terms. So let's say I've just split it into two sequences. And suppose they both converge to the same limit. Then is it true that the sequence also converges to L?
Yes.
Yeah. Why?
Like if you have some epsilon, then if for each of these we can find whatever that n is, and then take the maximum.
Hello?
Exactly.
I
Yeah.
guess it doesn't. Like if you take the increasing subsequence of some sequence A, then like if you take some sequence like 1 minus half, 1 by 4, minus 1 by 8, and
But this
so on.
converges to 0.
But wait, I am trying to get a like 1 minus,
Yeah, I
like
get it.
if
You're
some
doing 1
converges,
minus half, 1
like
fourth.
if
Fine.
some converges to some k and some converges to some minus k.
It's the same L.
Oh, I'm saying about k and minus k. Like there was some
Both these
sequence you
both
discussed
these
about.
Wait.
both these sequences are part of this parent sequence, so they should converge to L.
Yes, but sorry, Anurag, can you go on?
Oh, so the like if there is some subsequence case, so you are also denoting like some left terms of A without that subsequence.
No, but I've used every term here, right?
Oh yes, yes, then it is okay.
Yeah. Yeah. So
Yes,
if I skip only finitely many terms, even then it converges. So if even if A1 was not written here, it converges. But if I
it
skip,
doesn't work for infinitely many terms.
yes, because then I can make that converge to something else, right? So the point here is that if I intertwine two sequences that converge to the same limit, then even this intertwined sequence converges to the same limit, right? So if I have a sequence A1, A2, A3 converging to L, if I have B1, B2, B3 converging to L, and then if I intertwine them somehow in order like A1, A2, B1, A3, B2, like just intertwining the sequences, then even this intertwined sequence converges to L. As long as you use alt, well, it doesn't matter actually. Yeah. Okay. Great. Yeah, you should use all terms there. Yeah. And so now the natural extension is this. Suppose I have okay, so suppose I have, let's say I take the odd terms and this converges to L, and then I take the terms that are 2 mod 4. So which is the highest power of 2 is 1. Right. Uh, this converges to L, and then I take terms which are 4 mod 8. I just partition them into the highest power, right? So on, right? And so these are like a sequence of infinitely many sequences, right? So then I'll have A8, A24, etc., and then A16, A48, etc., right? So suppose they all converge to the same limit L. Is it true that A1, A2, etc. converges to L?
Yeah, the same proof works, right?
Think about it. Okay, so what do you do in the proof?
Oh, the- this will span like the entirety of the sequence
Yes.
overall.
We can try to prove it by epsilon definition easily.
Oh, okay. Because it could, when you take the maximum, it could tend to infinity.
Yes, you can take the maximum of that n
But
epsilon.
you can't because there
Yes,
are
yes,
yeah. So there's no
yes,
max here because there we
yes,
don't have
yes.
finite limit. Yeah.
It doesn't make any sense here of
Yes.
taking max.
Yes. I mean, if you could take max if it existed, but it doesn't exist here. We're just doing this. So for the person in the chat, we're doing this problem where we have these sequences A1. So we have a sequence A1, A2, A3, etc. And so now all odd, if you just take the odd terms, then it converges to L. If you take the terms that are 2 mod 4, so these are all 1 mod 2 terms. These are 2 mod 4 terms. Indices, that is. So 4 mod 8, 8 mod 16, etc. If all of these converge to the same limit, then does the sequence also converge to the same limit? So if it does, then you have to prove it. If it doesn't, you just have to find a counterexample. Okay, so it might be a little confusing in this sense, but think of these as independent sequences. And because we're just intertwining independent sequences, right? So like you can just take any. Okay, I'll just give you some more time to think. Any ideas?
We can take like the first sequence is 1, 1/2, 1/4, 1/8. Second sequence is 2, 1, 1/4, like, and then the next one is 4, 2.
Yeah, sure. That those are the counterexample, right? Yeah, you're right.
Yeah.
In fact, we can just start all of them with ones. That's also fine. So here's the idea. So take this. Okay, sorry. Take this to be 1, this to be half, this to be 1/4, or 1/3. It doesn't matter. I'm just taking the geometric sequence this time, and I can define this to be. So I'm just defining a sequence, right? And the answer is no, by the way. So I'm trying to find a counterexample, and this is enough for a counterexample. 1/4, etc. So now note that each of these terms, each of these sequences converges to this limit 0, right? But now look at this sequence: A1, A2, A4, A8. This subsequence. Note that every term is 1, right? So this converges to 1. So therefore, our initial sequence has some subsequence converging to 0, but we have another subsequence converging to 1. But that doesn't make sense, because if a sequence converges, then every subsequence converges to the same limit. Note this theorem. And so we have a counterexample, right? because we have this subsequence converging to 0 and this converging to 1. So we violate this theorem, right? And so A1, A2, A3 does not converge, right? So therefore A1, A2, A3, A4 does not converge. Because if it did, then every subsequence would also converge to whatever that limit is. And so we'll get 0 equal to 1 because this is 0. Does not converge. Okay, great. Here's another question. So this question actually leads to great properties for series. Okay, so before that, let me demonstrate you this question and then try to do the theorem. Yeah. Third plus 1/4. That's a
Oh,
second.
is this related to that homework problem you gave?
Yes.
Oh, it was a very nice problem, I
Yeah.
guess.
So I just want to revise that because then there are many properties of series that can be done using this. So
Oh,
okay.
yes, yes.
So does this converge or diverge? So what do you think? So first of all, we know that things like geometric progressions, etc., converge, right? So we have seen stuff like this somewhere before, right? This converges to 2 because it's the sum of a GP, right? So this is A, this becomes A upon 1 minus R, where A is the first term and R is the common ratio. So this is 1 over 1 minus half, which is 2. But then what about this? And also if the sequences are non-decreasing, say if I have 1 plus 2 plus 3 plus 4, this diverges, right? Uh, not minus 1 over 12. So I'll not make that joke here right now, even though I did. So, yeah, but then what about something like this? Yeah, so I think I should just mention this is definitely not minus 1 over 12. Yeah, so what about this? 1 plus half plus 1/3 plus 1/4. So how many people think that this converges? And how many people think that it diverges? I think it's a good question to ask.
No, it doesn't converges, it diverges.
Okay. Two more people
Can we
think it
argue
diverges.
like if this sequence were to actually converge, then we would have written it as 1 plus 1/2 plus 1/4 up to infinity times 1 plus 1/3 up to infinity, and that way the product of all like sequences having the a equals to 1 and r equals to 1 by p, where p is a prime. But then that would lead to like that would tend to infinity as the number of primes we incorporate starts increasing. So it like if it converges, we can't actually find a value to it. So
Wait,
then it
so
must diverge.
so wait, what did you do here? So we have this. Can you just tell me your argument once more?
If this sequence were to converge, then
Okay.
we could have written it like uh, as product p is a prime, 1 plus 1 by p plus 1 by p square, and that way that entire GP it could
Yes.
proceed, right?
Hmm.
Now this in now for each prime, the value of this sequence would be 1 over 1 minus 1 by p, so p over p minus 1, which is greater
Yes.
than 1.
Okay.
And since we're taking an infinite number of primes, this product would inevitably be like infinity.
No, but the
So
product of infinitely many terms that are greater than one can be finite. So because say I can have something like um uh, something like uh, so I could have something like
You can consider the Euler's constant.
sure, but just something. So, well, Euler's constant.
You just consider 1 plus 1 by n
That
raised to the n. That every term is greater than 1, but it still converges to some irrational number,
wait,
e.
which term? But that's the sum of terms.
No, like we have e is equal to limit n tends to infinity, 1 plus 1 by n raised to the power n. Then we
No,
can
but
open it as a product.
no, but we're changing the terms here. Here we're just multiplying another term to something that already exists. So there we are changing the term from 1 plus 1 by n to 1 plus 1 by n plus 1. So it's a little different.
Yes, okay.
Yeah. So think about this. So over 2 minus 1 by n. If I define this as an, then note that a1 times a2 times up to an is actually just 2 minus 1 over n plus 1. And so this tends to 2. But each of these terms is more than 1.
Okay.
Yeah.
Get it.
We can prove it by that homework problem you gave.
Yeah, but but this actually does lead to a proof. It's just
I
that need to be a
can
little
I
more
try
subtle.
to give another proof?
Yeah, just
Like you can
so
consider some sequence sub series 1 plus half plus 1 by 4 plus 1 by 8. Then we can consider 1 by 3 plus 1 by 9 plus 1 by 27 plus 1 by 81 and so on. But these all converge to different L's.
no,
So
but
if
this is
this
a
were to
series.
converge,
I mean, this is not a sequence, so it's not the same thing. I'm looking at sums here, right? So because
yes,
by that logic, 1 plus half plus 1/4 plus 1/8, I can divide it into subsequence that whose sum is different, right? But this converges. So note that this plus symbol changes things. It's not exactly the same thing. So for example, if I take like alternate terms, then this converges to 1 by 3. But then if I take these terms, this converges to 1 by 6. So these are different, but the total sum is still
I
half.
guess I can give some another proof.
Yeah, the homework proof.
Just then note that 1 by 3 is greater than 1 by 4.
Yes. Yeah, that's the
And
idea.
that, yes, yes.
Yeah.
That's the same idea like that problem.
Yes, exactly. So it's a nice property. Uh, keep primes which are infinite. Uh, yeah. Okay. So here's a proof that just avoids primes altogether because there are proofs that involve prime numbers. Here's the idea. Note that the sum of these two terms is more than 1/4 plus 1/4, right? Which is half. And then note that sum of these four terms is more than 1/8 plus 1/8 plus 1/8 plus 1/8, which is half. And then the sum of the next 8 terms is more than half, etc. And so if I take the first 2 raised to n terms, then the sum of the first 2 raised to n terms will be at least uh, n minus 1 times half, right? Which is more than n by 2. The first of the sum of the first 2 raised to n terms is at least n over 2, and that's sufficient to prove that this sum diverges, right? And so we get this sequence is at least 1 plus half plus half plus half plus half, etc. Actually, that's a good question. So the answer is actually no. Um but associative, I'm not sure what that means. But if you're saying that I can change the terms of the sequence and still expect convergence, then that's not true in general. It's true if all terms are non-negative. So, but it's not true if there are negative terms involved. But we'll not get into that right now. So maybe the next class we can look at that. Sorry. So notice the idea. The idea is to take these sort of terms and then club them together and provide a lower bound. So based on this, here's the question. Suppose I have a sequence A1, A2, A3 satisfying this. So it's a non-increasing sequence, lower bounded by 0. Prove that A1 plus A2 plus A3, so on, converges to some limit if and only if A1 plus 2A2, okay, so yeah, 2A2 plus 4A4 plus 8A8 converges. Yes, good. A2 plus A3 is less than equal to 2A2. That's one idea. Yes. Uh, yes. So it's the same idea as what we had done before. So here's the idea. Notice this. So A1 plus A2 plus A3 plus A4 plus A5 plus A6 plus A7 plus A8, etc. And now notice that the sum of these two terms is less than equal to 2A2, right? Because A3 is at most A2. And then the sum of these four terms is less than equal to 4A4. And then the sum of the next 8 terms is less than equal to 8A8. So we already have something, right? So we have that that okay. So yeah, we'll just keep it this way for now. So then what does this mean actually? So which direction does this prove? Uh, yes, yeah. So this is what this proves. So let's do this direction, right? So suppose A1 plus 2A2 plus 4A4 plus 8A8 converges. Suppose this converges to some L. We want to show that the original sequence also converges. But here's the idea. Note that I can look at this sequence as a series and look at its limit. Remember? That's what it means, right? To look at the sum of an infinite series. But now note that this is a non-decreasing sequence. Why? Because each term is non-negative. So each term is at least as much as the previous one. And note that this is bounded above by L. Bounded above by L. Because if you take only finitely many terms A1 plus A2 up to AN, it will be less than equal to A1 plus 2A2 plus 4A4 plus up to something, right? Some 2 raised to K times A2 to the K, right? And then that is less than equal to L. So then this is bounded above by L. And so remember the first property, a non-decreasing sequence which is bounded above converges. So this means A1 plus A2. Uh, so A1 plus A2 plus A3 also converges. It need not be L, but it will be something which is at most L. And what about this direction? So similar proof, similar idea. So
Just
yeah,
multiply the upper sequence by 2, then we will have a test greater, and then just we can easily get an upper bound into it.
yes, yeah. Let others just figure it out once more. See.
We can group the terms as A1 plus A2 greater or equals to 2A2, A1 plus A2 plus A3 plus A4 greater or equals to 4A4. And so the sequence 2A2 plus 4A4, like that way when it continues, it's upper
Well,
bounded.
you
And
repeated terms, so that's not fair, right? You shouldn't repeat terms because then you'll get some like if you use A1 plus A2 plus A3 plus A4 and then again use A1 plus A2, then the original sequence is disturbed. But you're close.
okay.
So just use A3 plus A4 at least to A4, right? So can you try to continue the solution? So okay, I'll just write that down. So so note that this is more than equal to 2A4. This is more than equal to 4A8. this is, well, it's equal to A2, and this is, just for the sake of it, more than equal to A1 by 2, etc. And so now note that this sum is half of this, right? And so now suppose A1 plus A2 plus A3 converges to L, then note that A1 plus 2A2 plus 4A4, let's go on till 2 to the k, A to the 2, A2 to the k. Then note that this is less than equal to A1 plus uh, um, A1 plus A2, sure, plus okay, let's keep it as 2A2, and then this is like less than equal to 2A3 plus 2A4, and then note that 8A8 is less than equal to 2A5 plus 2A6 plus 2A7 plus 2A8. Also, A1 is less than equal to 2A1, so I can write that. And then note that 2 to the k, A2 to the k, is less than equal to twice the sum of the previous terms from, okay, so basically I can write this as less than equal to 2 times A2 to the k minus 1 plus 1 plus so on to 2 times A2 to the k. Right? So it's less than equal to twice the sum of the first 2 to the k terms. And so this itself is bounded above by 2L. And so again, we have this sequence A1 plus 2A2 plus 4A4, which is bounded above by 2L. So this cell is different from this cell, by the way. So maybe I should write it as L prime, maybe. And again, it's non-decreasing because each AI is at least 0. And so this also converges. And so we've proved this. The idea is that this sequence is bounded below by this and bounded above by twice of this. That's the idea. So we've proved this. And now note that we can just directly, okay, so the motivation for this proof, well, I don't know what proof motivated which one actually, but we can just apply this to this sequence 1 plus half plus 1 third plus 1 fourth, right? So 1 plus half, okay, so 1 plus half plus 1 third plus 1 fourth converges if and only if 1 plus twice the second term plus 4 times the fourth term plus 8 times the eighth term converges. But this is just 1 plus 1 plus 1 plus 1, etc. But obviously this does not converge. So this does not converge. Yeah, is it clear? And okay, so here's another question. So find all reals R such that 1 plus 1 over 2 to the R plus 1 over 3 to the R plus so on converges. Well, it's zeta R, right? Not zeta 2. But yes. Oh, and oh, for the previous question, yes, you're right. Instead of 2, 4, 8, I could also have taken 3, 9, 27. The same logic works. You're right. So we saw, okay, so yeah, it's sort of just an application of the theorem, right? So it sort of follows directly from the previous theorem. So I'd like for everyone to try to speak up. So anyone who's not
Like
spoken
we can
before.
consider that sequence of
No, wait,
A.
wait, 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 wait. Anyone who's not spoken before. It's just that since the class is not very interactive, other than a few people, I don't get feedback whether it's clear to people or not. So then it's not clear whether the whole point of teaching is being conveyed or not. So okay, fine. So yeah, Anurag, go on.
And like you can consider that sequence that you proved for A and by A and N to 2 A 2 to the N into
But
2.
is that applicable for all R? So remember that we need the sequence to be non-decreasing, non-increasing.
It is non-increasing,
Why?
but it only works for some R greater than 1.
No, but um, we applied it to one, so it does work for things more than
Like if
other.
you take some R smaller than 1,
Even
or
then, like 1 over
like
root 2
it doesn't
is.
work for negative R in C. For negative
Wait,
R, it does just become
yes, yes. So for r less than 0, we cannot apply it, right? So for r less than 0, you need to argue separately.
like
So
we
how do you
argue that
argue?
if R is smaller than 0, then clearly take some ij where I is greater than j, then 1 by I to the R is clearly greater than 1 by j to the R, but 1 by I to the R lies should have been smaller than 1 by j to the R.
Why? I mean, I could have convergent
Because you just
sequences, series where which are not non-increasing.
because you just we just use the definition that it should be non-increasing.
No, but that's no, a series may not be non-increasing. That's for to apply the theorem.
Oh,
I
I'm
still
talking
need
about
to,
the terms in the series, like the
yeah, the
terms.
terms are okay. Yeah, the terms are sure. The terms may not be non-increasing. Sure. What does that say about convergence?
Is a topic in the hand.
Yes. So just as an example, I could have something like this, right? The terms are neither non-increasing nor non-decreasing, but there's still converges to 2/3, right? Yes. Hello. So yeah. So why does it diverge for r less than 0? Just note that every term is at least one, right? So so 1 plus 1 over 2 to the r plus 1 over 3 to the r is at least okay. Is at least 1 plus 1, so on. So this diverges, right? And now for r more than 0, you can apply the theorem. Right? Yes, it's it's a non-decreasing sequence, which is well, the sequence is bounded, but sure. I mean, I get what you mean. So, yeah. What about r more than 0?
Like then you can consider that sequence an by a2 to the n into 2 to the n, and then
Yes.
just each term. If r is smaller than 1, then each term becomes greater than 1.
Yeah. I think in the chat you're considering just integers. We need to show it for all reals. So the whoever's answering are at least 2, you need to also argue about 1.1 and 1.01 or something. Right? So, okay, here's the idea. Yes. So a 2 to the n times 2 to the n is equal to 1 over 2 to the rn times 2 to the n, which is 2 times n 1 minus r, right? And so this series converges if and only if this series converges. So should be um, there we go. 1 plus 2 to the 1 minus r plus 2 to the twice of 1 minus r plus etc. Right? And so when does this converge?
This converges if and only if r is greater than 1.
Yes, because if r is less than equal to 1, then this is clearly a GP, and if r is less than
Yes,
equal to
all
1,
terms become greater than 1.
yes, exactly. And if r is more than 1, then the ratio of this GP is less than 1 and more than 0, so it converges. So this converges if r is more than 1. Yeah. And that's it, right? So basically, 1 plus 1 over 2 raised to 1.1 plus 1 over 3 raised to 1.1 also converges. But the moment you hit 1, it diverges. Great. Um, okay. Here's another question. Fine. Okay. Sorry. Does 1 over 2 log 2 plus 1 over 4 log 4 plus 1 over 8 log 8 converge? The log is base e, or rather actually find all r such that converges. Oh, sorry. I don't know why I skipped terms. It should be 3 and 4. Sorry, this should be 3 log 3 plus 4 log 4 plus 5 log 5, so on. So you just need to apply the theorem, right? Again, yeah, okay, let's try it. Well, that can't be true, right? R less than what? I mean, if some R works, then everything at least R also works. So your set cannot possibly be like open in the other direction, right? I mean, it should probably be open in the positive direction.
Or greater than 1 as well.
Yeah, R greater than 1 works. Yeah. Yeah, why?
Yeah, if I haven't mentioned it, you just apply the same theorem, you get that this converges if and only if 1 over log 2 to the r plus 1 over log 4 to the r dot converges, like
Yes,
only the powers of 2. And the powers of 2, if it's like 2 to the n, you can take the n down and then log 2 out common. Like the 1 over log 2 to the r factor doesn't matter, then it's just 1 over n to the r, and we already did that.
exactly. Yeah. So first of all, note that for R less than or equal to 0, note that this is at least half, this is at least 1/3, etc. And so now this is bounded below by this harmonic series, which we know diverges. So we know that this diverges. Uh, what about R more than 0? Now for R more than 0, we can apply the theorem because this is at least this much is at least this much, so on. And now how do we apply the theorem? Uh, well, note that we start from 2, but it doesn't matter if I add a 1, right? It it doesn't really matter if I take 2 times a2 plus 4 times a4. If I consider this the second term, nothing really changes because I can just add a bogus term in the beginning. So I can just do that and get. So okay, so what is a2 to the n times 2 to the n? It's 2 to the n times 1 over 2 to the n times log 2 to the n raised to r. Yeah. But fortunately, this cancels. And since log 2 to the n is n log 2, I can write this as 1 over log 2 to the r times n to the r. And therefore, we will be looking at this new sequence, which is 1 over log 2 to the r plus 1 over log 2 to the r times 2 to the r plus 1 over log 2 to the r times 3 to the r, so on. Right? But note that this log 2 raised to r is a constant term, right? Because r is something fixed. So I'm fixing an r and then analyzing, right? So since this is fixed, this is some constant, I can just take it out and view the sequence 1 plus, so this is constant. I can just view the sequence 1 plus 1 over 2 to the r plus 1 over 3 to the r, etc. But we know that this converges if and only if r is strictly greater than 1. And so the answer is again r more than 1. So again, the answer is r more than 1. And this pattern actually sort of repeats. So if you consider this sum 1 over n log n log n, here you might have to take n at least 3 or something raised to r, and s at least 3. Then again, this converges if and only if r is more than 1. You just apply the theorem twice. Right? So note that here also we'll actually be applying the theorem twice. So from here to here and then from here to the next step. So here we'll apply the theorem thrice. And then again, so this converges if and only if, and then again, we can do it for r more than equal to whatever this. So I just need to make sure that the logs don't become 0 or something, right? Or not defined. So whatever this is, n, let's just take 100 for safety. Log n, log n, log n, raised to r, converges if and only if r is more than 1. Right? So it's quite neat actually. Basically you can always sort of this. So basically, this proves that there is no such boundary function for which everything above that function converges and everything below it diverges. There's nothing of this sort. Or rather, everything below it converges and everything above it diverges. So actually, there is nothing of that sort. And this is sort of the idea of why that's true. So, yeah. So the notion of boundary is vague, and the point is that there is no matter how we try to make this notion of a boundary precise, there is no such boundary. So that's the takeaway, actually. Okay, so we've seen lots of such convergence things, and great, and it's 8:24. I think we can go until 9, hopefully. But let's just look at one or two problems with sequences which have come in the past contests. The next time we'll actually do mainly only problems. So yeah, good. Okay. Here's one question. Uh, I have a strictly increasing sequence of reals such that okay, and that's it. Prove that. Okay, wait. A non-negative integer. There, a natural number n is said to be good if an is less than a naught plus a1 plus up to an minus 1 over n. Sorry, this goes on to n, and this is less than equal to an plus 1. Prove that there is exactly one good natural number. Don't spoil the solution if you've seen this before.
Is it up to n or n minus 1? Like, because there are n terms and n in the denominator.
Yes, so it's the sum of n plus 1 terms and there's n in the denominator.
Okay.
Yeah. It's not the average of something.
Can
So
I
the
say it? Yeah.
no, let's wait for others.
Okay.
So first of all, notice that this condition and this condition are actually not so different, other than the sign. So can you manipulate one of them to create the other? So well, with the opposite sign in some sense.
Yes, sir, it's doable. Like if we take the sum a naught plus a1 plus up to a n plus 1, we can write it as n times a naught plus a1 plus up to a n by n plus a n plus 1 whole divided by n plus 1. Yes, sir.
Yes,
So,
exactly.
yes, sir.
So
Since this one is less or equals to n minus a n plus 1, so the final thing would also be less than or equals to n plus
yes, you're right. So here's the idea. Note that okay, so first of all, notice that a1 plus up to an over n less than equal to an plus 1 is the same as saying that um, a naught plus a1 plus up to an plus an plus 1 over n plus 1 is less than equal to an plus 1. And this condition is basically this condition with n replaced with n plus 1 and the sign reversed. And so all we are trying to prove is that that there is exactly one n for which this holds and this does not hold, right? This no, so should write holds does not hold. So hopefully that makes things more convenient to handle. So you only sort of need to analyze this inequality and not both sides. So and yeah, because if you analyze one, you're sort of analyzing the other as well.
Yes, I got it.
Okay, wait, let's wait for ours.
I wanted to ask you something.
Uh, does it spoil the solution?
No, no, no.
Okay.
Did you and Iman give IMO at the same year?
I was in 2015. I don't think he was in 2015.
He was in 14, I guess,
Yeah,
because this was some 2014 problem only.
I see. I don't remember the source. So let's say that an n is okay. So I've used good here. Let's say that an n is nice if this holds, right? So so basically I need to show that there is a unique n for which we transition from nice to not nice, right? So yes. So what do we know is already nice? So is one nice? So is n equal to one, n equal to two, n equal to three, etc. Is one nice? So we say that n is nice if this holds. So I'm asking if one is a nice natural number.
Yes, one is nice.
Yes, because
A1 less or equals to A naught plus A1.
oh have I not? Maybe it is non-negative. I'll need to check. Wait, maybe it is positive. Uh, sorry, I think I missed this condition. Yes, it's positive integers. I totally positive reals. Positive reals. Actually, it seems that, okay, positive reals is fine. So I think the original problem had integers, but I think it holds for reals. Okay, it's fine. So positive real. So it is nice because a1 is less than. Sorry, it's my fault. I didn't mention positive. So it is nice, right? What about 2? Is 2 nice? That depends, right? What does it depend on?
If and only if A naught is smaller than 0.
No, that's not true. I don't think you can remove a2 from the
No, sir,
equation.
it's not nice. Because if n is nice, then n plus 1 won't be nice. We can just show that.
Uh,
But our claim extends to if n is not nice, then any number is not nice.
wait,
Any
wait,
other.
wait. You're spoiling the solution. Wait.
Okay.
Keep calm. Yeah. So sorry, Aditya, can you say that once more?
Sir, if n is nice, then n plus 1 won't be nice.
Why?
Like, if n is nice, like a n less or equals to a naught plus a1 plus up to a n by n, then we just showed that a naught plus a1 plus up
No,
to
we
a
did
n
not
plus
show it.
a.
No. We just said that this condition is equivalent to this. We've not said
Okay,
anything of
okay,
that sort, right? So
okay.
no. I'm just saying that this is equivalent to this. All that's all we've claimed. We've claimed nothing of that sort.
Okay, sir.
Yeah. So is n equal to 2 nice? So let's see. Yeah. So what do we need for niceness? We need this, right? Which is if and only if a2 is less than a0 plus a1. In which, but unfortunately, we don't know this. So we don't know if this is true or not. Right? But okay, so let's take cases, right? Suppose this is not nice. Then what can we say? Then we've already found a good index, right? Because we've already found an index such that this is nice and this is not. That's what we want, right? We want consecutive integers such that the smaller one is nice and the bigger one is not nice. Right? So then what can we say about, but the problem is that maybe somewhere later we get lots of not nices and then a nice and then again a not nice. So then we are violating the fact that there's exactly one good natural. Wow. We found one, but we need to show that there are no others, right? So, okay, let's say 2 is not nice. Then what can we say about 3? Is 3 nice or is it not nice? So try to figure that out. So is this true? So suppose this is not true, right? So suppose A2 is actually at least A0 plus A1. Then what can we say about this? Is this true? Can this be true? Why? So someone said no. So why is it that? Why is it the case? Leads to A2 less than A3. Exactly. More than A3, more than equal to A3. A2 less than A3 should be true actually. Uh,
A2 should be greater because we already have a definition.
yeah, A3 is actually more than A2. So I mean, leads to A2 less than A3 is not a contradiction actually. Nevertheless, we actually show that this is true. Uh, so we'll actually show that this is false, which is to say that uh, this is true. So why is this true? Because okay, you're saying that it sort of yeah. So you're saying the opposite thing. Yeah. Okay. Yeah, you're right.
You can use A0 plus A1 plus A2 is greater than 2A2.
Yes.
And then
Exactly.
just, yes, okay.
Exactly. Yeah. But this is actually true because note that 2A3 is more than equal to 2A2, which in turn is more than equal to A0 plus A1 plus A2 because of this, right? And so this is actually true. The point is that the first two terms is at most A2, and then 2A2 is at least at most 2A3. And so
Yes, it does.
again, 3 is not nice. And then now let's show that 4 is also not nice. It's the same process, right? So note that A4 is actually more than equal to A0 plus A1 plus A2 plus A3 plus A4 by 4 because note that the sum of these three terms is at most 3A3, which in turn is at most 3A4. And so this whole numerator is at most 4A4. And so this is true. So again, so I should not put a tick. I should say that it's not nice. And so 4 is not nice. And then the point is that if n is not nice, then even n plus 1 is not nice. Exactly. So the idea for this is exactly that. So
So we can induct then.
yeah, we can just induct. So you don't even need to induct. Yeah, I guess you need strong induction. No, you don't need strong induction. Yeah,
Or you
you
just
just
prove it for some general and
yes.
then
It's just true for
yeah.
any n, right? If
Yes.
n is not nice, then n plus 1 is not nice. And here's the proof. Suppose an is at least a naught plus a1 plus up to an by n. Then what does this imply? This implies that an plus 1. So, okay. So then we need to show that a naught plus a1 plus up to an plus 1 over n plus 1 is at most n plus 1, right? But note that the sum of the first 10 terms is at most nan. And this in turn is most this much, which is equal to an plus 1 as desired, right? Great. So we've shown that if some number is not nice, then everything else is not nice. So if 2 is not nice, then everything after it is not nice. And so we have a unique n, right? So which is great. So now suppose now suppose one is so we know that one is nice. Suppose two is nice, and then three is not nice. Then again everything after it is not nice. And so we have this unique index two. such that there's a tick and then a cross next. Right? That's what we want, a unique n. Right? So suppose 3 is also nice. Then if 4 is not nice, then we have the 3 as a unique index, etc. Otherwise, the only case that is remaining is if all natural numbers are nice. That's also something that we need to disprove, right? So what if all naturals are nice?
You just prove it for some consecutive to and then you do that.
So yeah, so maybe we need positive integers for this part. So I'm not sure if positive reals is enough. Let me think. Yeah, maybe positive integers is correct for this part. Yeah. Yeah. So what happens if all naturals are nice? Yeah. Sorry, you were saying something, Anurag.
Oh, I was saying to make a claim that if number k is nice, then k plus 1 is not nice.
Well, that can't be true, right? I mean, I could have one and two both nice. So yeah. So we just need to disprove this. So need to disprove.
Shourya, maybe try to wrap this up.
Yes. 5 minutes more.
Sure.
Like take 2 and 3 only and then just prove it that if 2 is then not, then 3 can't be.
That's not true because I can just take. No, yeah, it's not true.
Like NaN is greater than NaN is greater than equal to A1 after AN plus N because of the strictly increasing integers, and so that like builds up, and eventually it'll be bigger than A0.
Could you say that once more?
NaN is bigger than or equal to A1 after A1 plus after AN plus N, I think, or plus N minus 1, I guess, or plus something, and that when eventually that something will be bigger than A0.
I see. I see what you're saying. Yes, exactly. You're right. Yeah, that works. Good. So, okay. What is it that this condition is saying, right? So, over n. We need to prove that there is some n for which this is not true, right? So we need to show that there exists an n such that this is true. So why is this true? So okay, so the point is that if there were only n terms in the numerator with indices less than equal to n, this would have been true, right? But since there are n plus 1 terms, we can't just say that the RHS is the average of terms which is less than equal to n because this is an n and not an n plus 1. And so we just need to get rid of that average thing.
So we just then will have that A1 plus A0 plus A1 till AN minus 1 is greater than equal to some N A N N A.
We
Sorry.
should use less than equal to actually. Right?
Yes,
Because we
yes.
want to show this.
Less than
Yeah.
equal to N into AN minus 1.
Okay.
But it
So if you try to sandwich, okay, if you try to use the fact that the first n terms is at most n an minus 1 plus an over n, if you want to use this, then you'll need to show that there is an n for which this is true, right? But then what is this equivalent to? This is equivalent to this is more than equal to n over n minus 1. But that's actually not true because I can just take an to be something much larger than uh, this, right? So, for example, if I triple an every time, then this will be violated, right? So okay, so we can't just use that. The reason why it works is that the last term that you've left out is not negligible. That's the issue.
Suppose then we can take a n by n on the other side, and this we can get that a naught plus a1 till an minus 1 is smaller than equal to n minus 1 into an.
Okay.
By definition, we had that it was already smaller, then it was already like greater than.
Hmm. Okay, so let's just take some sequence of integers, right? Let's say three, I don't know, one, two, three, four, etc. Right. Okay, I guess I could take this. Sure. So I want this to be true, right? N over n. Well, I mean, we know that this is true because the RHS sort of behaves like half of n plus some. But yeah, maybe such examples are not enough to motivate the idea. Uh, yeah, I'm not sure. So, what if I start from, I don't know, 10? Does that change anything? Yeah, actually, just, I don't know, use your method to prove it. Just take time. Remember that we're talking about positive integers that are strictly increasing. So we actually have a naught plus 1 is less than equal to a1 plus 1 is less than equal to a2, etc. So we can use something more than just reals. Yeah. So, okay, here's the point, right? You're taking the smaller terms and taking their average. So instead, just take the larger terms, right? So that's the idea. So instead of taking the smaller terms, you can adjust to take the larger terms. So does that give you something? Okay, let suppose a naught is 1. Then is this true? If a naught is 1, then does there exist such an n? Okay. So notice that. Okay. So here's the idea. So note that the numerator is actually not the sum of n terms, but it can be written as the sum of n terms if you can club the first two terms, right? So if I can ensure that an is at least this much, then I'm done, right? Because then I'll be taking. So now the numerator is the average of n terms, where each of them is at most an, except for the first term possibly, right? But if I can ensure that, if we ensure an is at least an a naught plus a1, then we are done, right? So does there exist an n for which this is true? Again, remember we're talking about positive integers that are strictly increasing.
So a naught plus a1 greater or equals to a naught plus a1.
Exactly, that's it, right? So note that an is more than equal to n, right? Because a1 is at least 1, a2 is at least 2, a3 is at least 3. So if I can just take a naught plus a1, which will be at least a naught plus a1. And that's it. Another way of saying it, of doing this is this. So uh, note that, okay, so I have a naught plus a1 plus a2 plus up to an, right? I can sort of try to distribute a naught to these terms, right? So if I can say that this is less than equal to a1 plus 1 plus a2 plus 1 plus so on up to an plus 1, if I take n to be large enough, if I take n at least a naught, then this is true, right? And so, and now, well, okay. So maybe I should take uh yeah, okay. Well, okay, maybe I should take a naught plus 1 so that I have this and then an. And now this is less than equal to nan. This also works. I mean, anything of this sort works. Basically, these terms are much smaller than the larger terms, so I can just club some two terms, or I can sort of try to ignore the smallest term by sort of distributing it to the other terms. So here I've just distributed everything to a1, but I could distribute it to things. Okay, this does it. So the next class we'll only be talking about problems and then using some of the properties that we've seen more. Um, Actually, if you try to rewrite this, you can try to rewrite this as some sort of a sequence which is non-decreasing, which is strictly decreasing and is not bounded above. And so there is a point where it crosses some number, and so that and it's unique. So I'm saying it vaguely, but there is an idea like that. So if you can come up with that, it's nice. Otherwise, I'll tell you that the other way of looking at the solution.
Oh, sure, you're wrap.
Yeah, we're done. Yeah.
Okay, I'll end the thing, right?
Yes. Can you stop recording and I'll just wait for 5 more minutes for questions?
Should I stop recording now?
Yeah, you can stop recording.